All right, so what the chi-squared goodness of fit test is going to do is it's just going to check and see if a certain data set fits a distribution. So we'll try to test and see, like, if we were to take the last four digits of your cell phone numbers, we've talked about that in here before, and we took a distribution of the last four digits of your cell phone number, we would expect them to be uniform, right? We would expect the same numbers of zeros, ones, twos, three, four, five, six, seven, eight, nines, and tens. So we would expect a uniform distribution. So what a chi-squared goodness of fit test does is it actually lets us check and see if a set of data fits a distribution that we think it should. This is particularly helpful whenever you are, if you're dealing with a data set and you need the data set to be normally distributed, right? What you could do is you could go and you could check and see if the distribution you have fits a normal distribution. So you collect all of your data and you can say, hey, I really need this to be a normal distribution so that I can, use z-scores in order to calculate stuff here. So what you can do is you can use a chi-squared test for goodness of fit to see if your data set actually meets the requirements for a distribution. So that's what we're going to be doing here. Okay, so chi-squared tests is only used when we want to see if an entire data set fits a distribution that we expect. Okay, so it's a little different from the test that we've done in the past, where we were comparing two populations, comparing two proportions, means, all of those different things. Now, what we're looking to see is if this thing fits the distribution that we think it should. For example, right, if we throw two dice and we sum the numbers that are on the face, we would expect a distribution that looks like the one in this picture right here. Right? You expect more 7s than 11s. You expect more 6s than 2s, right? So you would think that the distribution would come out to be, something like this shape here, which is somewhat, normally distributed, okay? And on this side over here, you see the probabilities. And so we know whenever we throw dice, the probability of getting a 7 is 1 out of 6. You can see it written in fraction form on that side. That is the theoretical probability of getting a 7. So then what we could do is we could take, two dice and just throw dice, 200 times and record all the sums. And if we recorded all the sums, then we could go back and we could figure out whether or not the numbers that we got from throwing our die was close to, or we could say if it would fit the distribution that we would expect. So what we're going to be doing is comparing a sample distribution to an expected distribution. This is how many we expected to get. This is how much we actually got. Are those two things close to one another? Do the two distributions actually fit together, or are they different? So chi-squared test, you can see down here kind of the explanation. The main difference here that we're talking about is we're testing to see if an entire set of data fits a distribution. We're not checking to find a range that one statistic might fall in. Remember, that was a confidence interval. We said we would expect the mean to be somewhere in between here and here. And we're also not checking to see if two things are different or if they're statistically significant, if there's a difference that is statistically significant for two things. What we're doing now is we're checking an entire set of data to see if that set of data fits a distribution that we expect from it. So we might get to do some pretty good activities and stuff with this a little bit later on, but we just kind of want to lay the groundwork here and see if we can figure out what's happening. Is everybody okay with this right here? Everybody copy down what you need to. No need to have like every word written down for the example. It's just kind of a general idea of what's happening there with the dice. Okay, just like every other test that we want to do, whether it be a hypothesis test, a confidence interval, there are always certain conditions that have to be met. The first condition for chi-squared is it has to be counted data. Okay, so the values in each cell must be counts for categorical data. So we're talking about categories here more than we are, we're not talking about quantitative data anymore. We're talking about qualitative or categorical data. And the big difference here is even with the dice, if we had the numbers 1, 2, 3, 4, 5, 6, and 7, But what we're doing is, those are numbers, but that doesn't mean that they're not categorical data. Because all we're doing when we have the dice is we're counting the number of ones, the number of twos, the number of threes, the number of fours, the number of fives, so on and so forth. And so what we're doing there is actually categorical data, because we're just counting, the number of times that each sum shows up. There's also an independence assumption, so samples should be independent of one another. The randomization condition. So the samples have to be counted, that have been counted should come from a random sample. So whenever we start doing these, we have to make sure that we're still using a random sample. So independent random samples. And then the 10% condition is still in play. The sample must be less than 10% of the population. The only thing that's a little bit different is the expected frequency. Remember, whenever we're doing a population proportion, we have to expect 10 successes and 10 failures. But in this case, whenever we're doing a chi-squared goodness of fit, we have to expect at least 5 samples in each cell. So we'd be looking for 5 samples in each one of our cells to say that we should move forward with a chi-squared test. Okay, just a few more seconds to get those. So you can see a lot of the conditions are the same. There are always just some minor changes to the different conditions that we use. And so what we're going to do now is I'm going to give you a couple of formulas, and then we're going to start working through and just run a couple of chi-squared tests. We'll talk about how to do it in the calculator. And the chi-squared, remember, it is a distribution. It's a probability distribution, just like the normal distribution and the t-distribution. It lets you know the probability, you kind of have a curve, and remember the area under the curve is always the amount of probability you have of something happening. So we're just going to be looking at the curve and trying to decide how likely was it that we would get this sample. That's going to be the question, right? If we were shooting dice, okay, and the dice were fair, how likely would it be that we would get this distribution? Knowing that the theoretical distribution for dice is like the one we saw on the last page. So that's what we're looking for. Knowing that the theoretical distribution is like this, is it likely that we get one that is like, like our sample? And what we're doing is the same kind of thing with a hypothesis test. We'll say if the sample is, or if the null hypothesis was true, if the distribution was really supposed to look, like this right here, what is the probability that if we threw fair dice, that we would get something that looked like this, or it would be, let's make it even more extreme. What's the probability if we were throwing fair dice that you would get something that looked like that? Well, we can say, oh, that probability is not very good. So it would fail the chi-square test of goodness of fit. So we would say, hey, if the null hypothesis is true, if this is how the distribution is really supposed to look, then the odds of us getting a sample like that are very, very slim if the dice are fair. So our conclusion would have to be that the dice are loaded, they're weighted, they're not fair somehow, right? Tanzim. Counts. If they're trying to determine if it's categorical or quantitative, is just the counts, okay? So, for example, if we were talking about the number of siblings that people have in this class, I could do it either way. I could do it categorical, or I could do it quantitative. And here's the difference. If I said that I'm looking for the number of people in this classroom who have 1 sibling, 2 siblings, 3 siblings, 4 siblings, and then we'll say 5 or more, right? And I were to count each one. How many people have 0 siblings? You raise your hand and say, okay, 5 have 0 siblings. How many people have 1 sibling? Okay, 6 have 1 sibling, right? And so what I'm doing is now I'm counting the number that are in each group. The number of people who have 1, the number of people who have 2, the number of people who have 3, so on and so forth. And then, but I could turn right back around and say, all right, How many siblings do you have? How many siblings do you have? You say 0 and 1 and 2 and 3 and 4 and 5 and 6. And then, okay, 4 and then 2 and a 3 and a 1 and a 2. And you go through and you add them all up and you get an average. Well, now that's quantitative because you're talking about the quantity of siblings. But the first example would be qualitative because I'm assigning a number 6. And I'm saying anybody who has that number of siblings, I'm counting you and putting you in that group. So the easiest way to figure it out is the counting. Right? Right, because we're counting the number of times that we get a 7. The 7s aren't being used themselves as an average. We're just counting the number of times that a 7 shows up. All right, so the chi-squared statistic, this is how we'll calculate the chi-squared statistic. Think of this like a z-score or like a t-score. Okay, that's the way that the chi-squared statistic will work, and then we'll say, hey, what is the likelihood, with a z-score, what's the likelihood that you get a z-score of 3 or a z-score of 4? Like, well, the probability of getting a z-score of 3 or 4 is not that good. Well, in the same way, we'll look at a chi-squared score, and we'll say, hey, depending upon the chi-squared score, how likely is it that we would get something like that? If the chi-squared score is 5, is that big? Is that, a high chi-squared statistic? So all you do is you sum. So for each individual cell, what you do is you take the observed number of values minus the expected number of values. So if we were throwing the dice, we're going to throw the dice 10 times, and we would expect 2 7s, right? And let's say that we only got 1. So we expected 2, we observed 1. So this would just be, 1 minus 2 squared divided by the expected value, which would be 2 again, right? So then we would just do that for each individual cell, and we would add all of them together. Like the t-distribution, the chi-squared distribution depends on degrees of freedom. Right, so we have to talk about the number of degrees of freedom in a chi-squared sample. But here's the thing, with chi-squared, it's the n that we're going to use is the number of categories, okay? The number of categories. So if we were throwing dice, if I threw the dice 200 times, that doesn't matter, okay? The number of categories is what matters. So if we were throwing dice, how many different number values could you get? Yeah, there are 11 different possibilities, 2 through 12, right? So there's 11 different possibilities you could get when you're throwing dice. It doesn't matter that I did 200 trials. Okay, so when we're talking about degrees of freedom with a chi-squared statistic, it's not the number of trials, it's the number of categories. So with the dice, there would be 11 categories. So our degrees of freedom would be 11 minus 1, which is 10. Right, we'd have 10 degrees of freedom. Patrick. The number of different possible categories. So even if we never threw a 2, it was still a possibility. But remember, if we never threw a 2, what would happen? If our observed value in 2 was 0, is that good or bad? It's bad, right? Because our expected value for every category is supposed to be at least how much? 5. Right? The expected value for each category is supposed to be 5 or more. So if you had an expected value of 5 and you got 0, that wouldn't be very good. It's not very likely. But if you did get a 0 in there, you could still proceed, okay, as long as your expected value was supposed to be at least 5. And that category would still count, even though there was never a number that landed there. Okay, just wanted to show you what the chi-squared distribution looks like. Kind of like the t-distribution, it changes with the number of degrees of freedom you have. So if you have 1 degree of freedom, that is, this black line right here. So you can see the way the distribution looks. And as you add more and more degrees of freedom, more and more of the probability kind of moves out into the tail. Does everybody see that this one doesn't have a whole lot of probability out in the tail? But if you look at the pink one here that has 5 degrees of freedom, look at how much probability there is in the tail, right? So the more categories you have, the more likely you are to get some numbers out on the fringe, okay? All right, so let's actually look at an example. Go ahead and flip to page 698 in your textbook. and we'll talk about these together. Somehow my numbers got my letters got scrambled there. Yeah, we'll have to deal with that. Oh yeah. Okay. Here and here. Okay, you guys on page 698 in the textbook? By the way, page 698. This is the next to last chapter in the textbook. So we're going to do this one today. I'm hoping to do the last chapter tomorrow, and we're done learning new material. We have we'll have, the AP exam for you guys is 1 month from today. So we'll have basically the last month to review, kind of sharpen up on a few things, work on FRQs, and go from there. I'll go ahead and tell you this too. On Friday, your test on Friday is just going to be straight up multiple choice. I told you that the multiple choice exam is 40 questions, an hour and 30 minutes. So since you have an hour and 30 minutes in class, I'm going to give you a multiple choice section of the exam and just kind of let you see how well you could do on it right now with the proper amount of time, right? So everybody will have to go to fourth lunch on Friday. Because I'm not going to be here Friday, so I'm not going to make it super confusing and stuff like that. So everybody will just go to fourth lunch on Friday, and you'll have that test. So be ready for that. But multiple choice, 90 minutes for 40 questions, and you should know how to do everything. So it'll just be a complete practice test is what you'll get. All right. So looking at number 3 on page 698, I'll read it so people watching at home will know what's going on. Okay. All right. It says, after getting trounced by your little brother in a children's game, you suspect the die he gave you to roll may be unfair. To check, you roll it 60 times, recording the number of times each face appeared. Do these results cast doubt on the die's fairness? Okay, so what we're trying to see is whether or not this die is fair. We're talking about a single, one, so singular of dice is die. If this thing is fair, and you can see there the faces 1 through 6 and the number of times that each one came up. And I see now I need to get these two to separate. Okay. And for number 1, I forgot a 1 here. That's supposed to be 11. Oh, maybe it was already there. It was covered up like the other ones were. All right, so there's the face, the counts. So if the die is fair, how many times would you expect each face to show? So so what they're asking us to do is to calculate the expected value, right? So what we have to think about is the probability. If it's a fair die, okay, what is the probability of throwing a 1? Yeah, exactly. It's 1 out of 6. What's the probability of throwing a 2? And a 3? Yeah, all of these should be 1 out of 6, right? Because we just have 1 die. That's the probability of throwing 1. We're going to use the probability to figure out the expected number, okay? Yeah, not the expected probability. So for here, the count, remember how many times did he actually throw the die, or the die? So this count should be 60. The total probability should come out to be what? 1. All right, then our expected values. So if we're going to throw it 60 times, and the probability is 1 out of 6 for getting a 1, how many times would you expect to actually throw a 1? Yes, just 1/6 times 60, right? All you got to do is multiply those two together, and you get 10. And you find that the expected value for each of these is 10, which would give us a total of 60 throws, right? And then remember our formula. We want to take the observed number and subtract the expected number. So if we expected, or we threw 11 and we expected 10, so this is 11 minus 10 is 1. That category was off by 1. The second category, the 2s, yeah, negative 3. It was 3 below what you would expect. No, it won't matter once we square it, but we'll go ahead and put it for right now. Okay, these will matter whenever we start doing, we'll look at standard deviations for each category a little bit later, and whether it's positive or negative will matter whenever we look at standard deviations for each category. Yeah, we got 9, we expected 10, so we're 1 down. We got 15 and we expected 10, so we're up 5, 2, and then negative 4. And I'm not necessarily worried about a total for this one. Okay, so remember the next thing we said that we want to do, yeah, the residuals total should come out to be what? 0. The differences for all of them should come out to be 0. If you remember that about residuals. Remember, a residual is the difference in the observed value and the expected value, whether it be on a line of best fit or, in this case, with our categorical data. Because if you expected, this tallies up to how many throws? 60. And this counted value tallies up to 60. So in the end, if you go over in one category, you're going to have to go under in another category that same amount so that when you add those two numbers, you get 0. Okay? So now we're going to square these. So this is 1 and 9 and 1 and 25 and 4 and 16. So not really worried about totaling those either. All right, and so then, remember, our next thing was to take the observed minus the expected squared, so that's this category here, and divide by the expected value. So that's 1 divided by 10, so that is 0.1. What's this one going to be? 0.9. It's 9 divided by 10. This one's 1 divided by 10. It's 0.1. 25 divided by 10 is 2.5. 4 divided by 10 is 0.4. And 16 divided by 10 is 1.6. So what does this come out to be? Yeah, if we add all those together, we get 5.6. Okay? And so now you can pull out your calculator. And this is our chi-squared statistic, right? So what we're looking for is if we have, how many degrees of freedom do we have here? 5, because how many categories are there? 6. So for chi-squared, degrees of freedom is the number of categories minus 1. So we got 5 degrees of freedom. So our chi-squared distribution is going to look something like this, right? And what we're going to do is we're going to come out with a 5.6, okay? And we want to find the amount of probability in the tail. Remember, this is how likely we are. What is the probability of us getting a sample like this if the die is really fair, right? What's the probability of us getting a sample that's distributed the way this one is if the die is really fair? So I'm going to go on. And I'm going to go, let me get out of here. Second distribution. And I'm going to go to a chi-squared CDF. So you'll see the Greek letter chi squared there, CDF. And I'm going to calculate all the data from 5.6. Remember, I'm trying to go from 5.6 to where? And above. So what do you think I'm going to use here? 99. Do you notice anything about this distribution compared to the normal distribution, though? Can you say anything about the amount of data in the tail? Is there more or less in this one than the normal? More. The normal tail gets really, really what? Flat. And if you got a 5.6 as a z-score in a normal curve, how much would you expect to be from 5.6 beyond? Very little, right? So with this chi-squared statistic, 5.6, and there's still some stuff behind it. So what I'm going to do is I'm going to go to 1,000 on this one, okay? Just because there's more data. And if you want to make 1,000 the new rule of thumb, that way it doesn't have to change from one to the other, it'd be fine if you started using positive or negative 1,000 with your z-scores and t-scores and everything else as well. Okay, it'll be perfectly fine that way. So I'm going from 5.6 to 1,000, and the degrees of freedom I have is 5 degrees of freedom. You might know what this value is called? It's a p-value, just like it has been with hypothesis tests, right? So the chi-squared test still works a lot like a hypothesis test, but it's for an entire set of data. All right, so looking at number 3, we're going to skip part B. But what we did was we came up with the expected values. That was part A. Part C says to state your hypotheses. What would the null hypothesis be? There's no difference between the expected values and the observed. Really, very good. Which would mean what about the die? It's fair. That the die is fair. If there's no difference between the expected values and the observed, so H naught would say that the die is fair. You know, there's no difference in the expected values and the observed values. The alternative hypothesis would say that there is a significant difference between the expected values and the observed values. Therefore, the die would be unfair, right? So those would be our two hypotheses. And then part D says to check the conditions. Well, if we look at the conditions, what's the first thing that we're checking for whenever we look at the conditions? It has to be what type of data? Huh? Yeah, it's got to be categorical. Do we have different categories here for our data? Yeah. Okay. What's the next condition? Independence. Each time we throw the die, is that independent of what happened right before? Yes. Right? If I got a 6 last time, that doesn't have any bearing on what I'm going to get this time. So each of the rolls are completely independent, which makes it random, right? Because we're throwing a die, so it is random, so we don't have to worry about the randomness. What was the other one that we had to worry about? 10% of the population. Well, we could make the population as big as we want to with die throws, right? That's not as big of a deal. And then the other one is that we need to expect at least what? 5 for each category. How many did we expect in each category? 10. So our conditions are met, right? So all of the conditions are met. How many degrees of freedom are there? We already talked about that one. There were how many degrees of freedom? 5. It said to get the chi-square statistic. That was the 5.6. That's what we calculated right here, our chi-square statistic. And then it says obtain the p-value. Our p-value here is 0.347. Okay, so state our conclusion. What are we going to do? Very good. We failed to reject the null hypothesis. There is no evidence, right, that the die is unfair. I don't know. What p-value would we need to reject it? You need one that's really, really small. And they can tell you at different alpha levels, right? They can give you a level of significance in these just like they can any other hypothesis test. But in general, you know, we look for a really small p-value, something, you know, 0.05 or less before we would say that there's, remember, 0.1 to 0.05, okay, there's weak evidence, right? 0.05 to 0.01, there's some evidence. And then if it's less than 0.01, there is strong evidence with the p-values, okay? Cameron. It's the chi-square statistic. Yeah, the 5.6 is our chi-square statistic. No, it's just it's the chi-square statistic. It operates basically the same way that a z-score and a t-score does. It gives you a cut point where you can find a probability density, right, the area under a curve from one chi-square statistic to another. But in general, it's not called a score. All right, so this is what I want you to do. Everybody take a little piece of paper out, and I want you to write a number. 1 through 4. 5 is not an option, Tanzam. Yes, it has to be a whole number. So an integer, maybe I should put that in there. Write an integer between 1 and 4. All right. Just write it on a piece of paper, a little piece of paper, like tear it out and hand it to me. We'll take them all up. Okay, I've got everybody's number. All right? Okay. So, certain tests claim that if you have people do this, the proportions that they will give these numbers is this respectively. 10% will give you a 1, 20% will give you a 2, 50% will give you a 3, and 20% will give you a 4. So we're going to use our data that we just took here and test it. So I'm going to try to split these into groups real quick. Remember, we said integers. Who said 2.4? We'll just throw it out. It's a bad sample, which is a 2. I can deal with that. Two squared, that's a 4. There's a 4 and a 2. And here's a 4 and a 2. There's a 3 and another 3. Okay. So here's what we've got. I've got 0 ones. For 2s, 1, 2, 3, 4 2s. 3s, we've got 1, 2, 3, 4, 5, 6, 7, 8. And then we've got 1, 2, 3, 4, 5 4s. They run tests. Okay, so how many total people did we have here? 17, right? We had 17. So if we had 17 people, let's find the expected value, right? So so we had 17 people. So I'm going to say that n is equal to 17. Yeah, what's the expected value for a 1? 1.7. What's the expected value for 2? Yeah, it's just the probability times the number that we used, right? So that would be 3.4. For 3s, how many would we expect? 8.5. And then we would expect 3.4 4s as well. Okay? What's wrong with this right here? We need to expect what in each category? 5. So we'll proceed with caution, just so we can work this out. Okay, we're going to work it out. So we'll proceed with caution. Okay. Go ahead and take your calculator. We'll try to make this this easy on ourselves. I just want to show you how to do one in the calculator. These calculations I don't think would be too difficult, but we'll use them anyway. So everybody go ahead and go to Stat, Edit, and we're going to create a couple of lists here. So we'll just practice doing these calculations using the lists. And what I'm going to do is, in the first list, I'm going to put in the actual observed number. Okay, so we got 0 ones. How many 2s were there? I can't see it right now. 4. How many 3s? It was 8. And then 4s? 5. Okay. Then I'm going to jump over, and in L2, yeah, this is the expected values. So for 1, it was 1.7. For 2, it was 3.4. Then it was 8.5. And then it was 3.4. I don't think I got my 3 in here. 3.4. Okay? Oh, I didn't get a 3.4 on that one either. Thank you. This one should be 3.4. Enter. All right, so there they are. Now for L3, what I'm going to do is I'm going to try to get this. That's what I want out. Okay, so remember my original was my observed was L1. L2 is expected. And what I want to do is get observed minus expected squared over expected. So for L3, I'm going to hit enter. And I'm going to do it in terms of my lists here. So observed minus expected squared. I'm going to see if, can I use alpha y equals in here? Huh? So for this one right here, on the top part of my fraction, I'm going to open a parentheses, and I want my observed value. That's in L2. So I'm going to hit, or L1, I mean. So second, 1, and you can see the blue L1 over that. So it'll just put L1 in here. And I'm creating a formula. Make sure that you have the L3 all the way at the top highlighted like I do right now. And you can create a formula there that it'll work out for you. So I want to do L1 minus, and I'm going to use second 2, and that gives me L2. So second 2. Mine's not picking up. Second 2. There it is, L2. Close parentheses. I want that value squared divided by my expected value, and that is in L2. So second 2 will give me L2 again. And I'm going to hit enter. And you can see my different values there. And do they have them in fraction form? Because that first value is not right. Oh, no, it is good. That first value is right. It'll be 1.7 squared divided by 1.7. So it'll take you right back to 1.7. Gotcha. Okay, so I'm going to jump straight to my chi-squared statistic. Now, to get my chi-squared statistic, what do I need to do with these numbers right here? Sum them up. So I'm going to hit stat. I'm sorry, second stat, because we want to get into list. Hang on. Or is it in stat? Let me look right quick. Yeah, it's stat. No, that's right. It's second stat, and then you go over to math. Because second stat is lists, and then if you slide over to math, it'll tell you the list that'll let you do, the math that'll let you do with a list. And we want to sum up everything, and we want to sum up the stuff that was in L3. By the way, make sure you do this. I need to get out of here, so hit second mode and get out. Make sure you're back to this, and then you want to run that second list. Go over to math. And then we want a sum, that's number 5. And then we want the sum of what's in list 3. So I'm going to use the 3 right there, plug that in, and it'll give it to me. So there's my chi-square statistic. It's 2.588. How many degrees of freedom do we have? 3, because how many different categories were there? 4, so 3 degrees of freedom. So I'm going to go second distribution. I'm talking about a chi-squared cumulative, so it's a CDF. And I'm going from, here's my statistic. I'm going to put in my answer. All right, that last answer that we just got was our chi-square statistic, so I'm going to put it in there, and I want to go from there to 1,000. My degrees of freedom, though, are 3, and I'm going to paste that. Hit enter. And my p-value, 4.596. Okay? Is that a big p-value or a small p-value? It's really big, right? What's the largest p-value you can possibly get? 0.5. 0.5 is the largest p-value you can possibly get, because this means that 45% of the data would land that far away, right? But here's the thing, Tanzim. Think about it with a normal distribution. If I started saying like how far I could get this far or further, how often? If I go to the left side, what happens to my p-value? Yeah, so it splits it in half. Half of them are for the top, half of them are for the bottom. So the largest p-value you can possibly get is 0.5. So to have one that is 0.45 is very significant, right? So what would our null hypothesis be here? But what would state the null hypothesis? What would the null hypothesis be? Does anybody know? That the claim is true, right? The claim is true, that the distribution of, numbers that people would write down would stick with this, right? It would stay to these proportions. So the null hypothesis would be that this claim is true. So the claim about the distribution of numbers that people would give is true. The alternative hypothesis would be that the claim is false. Yeah, that the claim is not true. So that's our alternative hypothesis. And in this case, we're going to fail to reject the null hypothesis. So our conclusion would be that there is statistical evidence that this claim is true, right? There's statistical evidence that that claim right there is true, that this is the true proportion that people would respond with those numbers. Excuse me. Because that would be like kind of an expected value if we were doing something random, Ben. So if we were, if we just had a 4-sided die and we were going to roll it, we could say, hey, we would expect a 1 in 4 chance, right? But when you're dealing with people, is there randomness? No. You just saw it at play. People think they're random, but are people truly random? No. If I tell you to write a number between 1 and 4, you don't randomly pick a number, right? You think in your head, it usually goes something like this. Well, I don't want to pick 1 or 4 because those are the last numbers, and 2 is the next one after 1, so people would expect. So that's why teachers, if they make out a multiple choice exam, they usually put C, because well, you can't make the first answer the correct answer whenever you make out a multiple choice test. And then for answer choice B, well, you just got past answer choice A, so it's still too early to have the correct answer down there. And then you get to C and you think to yourself, well, I don't want the correct answer to be the last one, and so now I'm going to put it as C. And so if a human being makes out a multiple choice test like that, they will always make a inordinate number of the answers C. So one of the things that they actually teach us in education classes, right, at the university is whenever you make out a multiple choice test, what you're supposed to do is design distractors. So if you were to make an error somewhere in the problem, what number would you get, right? If I was talking about standard deviation and you forgot to take the square root, put that number in there as well to distract you. So you're supposed to create the possible answers that someone would get if they made a mistake, but then in order to make sure that you're not putting all the correct answers at C, you put them in order. The smallest number is A, the next number is B, C, and the largest number is D. Or if you're making a test in English, you put them in alphabetical order according to the first letter. So if you're looking at vocabulary words and there's like 4 I want to put down, I don't pick where I put the correct answer. I get the 4 words that I want to list for you to pick from, and I put them in alphabetical order. So now the word will, randomly be in different spots based on its place in the alphabet, not based off of when I wanted to pick. So the reason why we don't expect 0.25 in every one of these categories is because when it comes to people, it's not that random. This is a case in point right here, right? The number of people who pick 3s. So what we could do, Ben, is we could test. Well, let's run this. Is everybody okay? We're running another little experiment right here. Let's say that we assumed that people were completely random. Okay? If people were completely random, what would you expect each of these probabilities to be? All right, so let's rerun it. What's your expected value for 1s then? Huh? Expected value, Ben, not observed value. If we were gonna survey 17 people, and there's a probability that a fourth of them will give you a 1. Okay, so what's the expected value? Yeah, they'll all be 4.25. If you add all those together, that'll give you a total of 17. So let me get my calculator back up. And I'm going to go back into my list. Stat, edit. And I'm going to come over here to L2. And I'm going to change everything in L2 to 4.25. Didn't do it for me. 4.25. Enter. 4.25. Enter. I'm going to come over to L3. I'm going to get it, and I'm going to set up that same equation that I had earlier, right? Because it's got numbers in there. It doesn't save your equation. So we got to go back and put it in there again. So I'm going to use alpha y equals. Okay, and we want everything that is in L1 minus the stuff in L2. Second, 2. All of that squared over L2. Enter. Okay, so now I'm going to go to second list. Well, let me get out of here first. I need to get back to my normal screen, right? Second mode, quit. Second list math. I'm going to do math from a list, and I want to sum everything in L3. Okay, our chi-square statistic has changed significantly, right? Before it was 2.588, now it's 7.705. So let's go in and do second distribution of chi-squares CDF. And I'm going to make this my new answer. There, enter. And now my p-value is what? 0.05. So now there is strong evidence, almost, right? There, if it's below 0.05, we'll say there's, moderate evidence. But this right here, there is some evidence that we should do what to the null hypothesis? Reject it. And what was our null hypothesis this time? That people would be completely random. And if it was completely random when you're picking 4 numbers, what type of distribution do you expect? Uniform. Yeah, you would expect a uniform distribution if that was true. So when we tested this against a uniform distribution, the likelihood of people really choosing a uniform distribution is extremely low, according to this, right? But whenever we checked it against this test claim, it was extremely high. So people aren't so random, okay? So that is a chi-squared goodness of fit test.